our fabulous chemistry minions.
It's our favorite teachers,
Milks and...
MoNaCo.
Yeah, don't be calling us a dynamic duo or nothing.
This is one of my favorite parts of our unit. It's how batteries work.
Who I know personally it's one of your favorite parts of the year.
It's applied chemistry, and I just made a nice video I'm going to post up on my
Batteries.
Electrochemical Cell.
Nice. So let's figure out what those are. First of
Well,
all, we got two kinds. So voltaic is specifically the one that has the spontaneous reaction that turns stored chemical energy into electrical energy. These are the ones we're going to see the most, and there's a picture of it in the bottom corner.
There's a synonym for voltaic. It's electrochemical.
Right, and isn't it, could they say galvanic also?
Galvanic, voltaic, electrochemical, all three of these are the same.
Yeah, you might want to write one of those down, guys, because who knows how the region's going to state it.
All three are testable.
Correct.
Galvanic, not so much, but voltaic and electro and...
Now, electrolytic is a little bit different, and there's a Q, there's a hint right in the word, electro. It takes electricity
to make it go.
Because it's a non-spontaneous reaction.
We have to force these.
Right, and we just learned about these using Table J.
Just because a reaction is not spontaneous doesn't mean that we can't make it happen.
Sure,
we just have to
doesn't mean we might even want it to happen.
We'd have to force it to happen, and that's okay. That's called doing chemistry.
Yeah, we just got to give it.
Now, parts of the battery, which is really what's important about this video, are electrodes.
Okay, so I see some, and I see the word electrode
Twice.
right in that picture on the bottom right.
Now, an electrode is a generic term for any part of a battery that's metal that connects to the liquid or the ions in the circuit.
Okay, right.
So in this case, we have a positive and a negative electrode.
Correct.
Okay, every battery has a positive and a negative electrode.
Yeah, and they have the positive and negative ends.
Which actually have specific names.
They do.
They're called anodes.
Yes.
Anode is the electrode where oxidation takes place. This is where we lose electrons from the metal into the circuit that goes through the voltmeter or whatever.
Great.
The anode is always going to be the more active metal.
So there's another use for Table J. When I see the two metals, I can look up magnesium and I can look up copper on Table J, and magnesium is, whichever one's the more reactive metal is the anode.
And it also, since it is losing electrons, it loses electrons to the circuit, and we give it the negative symbol as a result. Anode, A negative node, AN node, anode.
Right. And we remember that the anode is where oxidation takes place with that anox.
Anoxygen. Yeah, anox, not red cat.
Anox.
So we'll get to red cat on the cathode. It's the other one. It's the electrode where reduction takes place. Because remember, you can't have one without the other. So the cathode is the less active metal. It's going to receive the electrons through the circuit from the anode, and as a result, it's the positive terminal.
There you go. And we can assign the actual half reactions to these, but I think we're going to wait and do that on the next slide. Okay? So,
and your practice is really good at that too.
Yeah, so we got that. Let's get to that piece. So now the direction of the electron flow is always going to go from the anode to the cathode. We remember that because A comes before C.
So it's alphabetical order.
Alphabetical order. A always comes before C, and it's the more reactive to the less reactive metal, because of course the reactive metal is the one reacting and giving off that electron.
It's more active, so it's easier to give up electrons.
Right. Salt bridge is important.
It completes the circuit. Any battery out there, no matter what, must have some sort of salt bridge. Because if your electrons are flowing through the electrical circuit powering your device, you got to have some ions to offset the flow.
It's got to be a circle, a loop, if you will.
And you hopefully have learned that for regular electricity too. You can't have a light bulb turn on unless the circuit's a loop.
Right.
The salt bridge completes the circuit inside the battery.
Correct.
So you don't ever see these except in Regents chemistry.
Right. Because you don't always see two beakers full of liquid making this happen either. That's not going to power your light at home. You just know
your battery's got a plus and minus end. This is all happening inside of your battery.
Correct.
All right, so let's write some reactions.
All right, so the basic oxidation reduction overall reaction is written for us down there. So notice the spectator ion has been removed. And on the reactant side, I got magnesium solid with copper 2 ion. And on the product side, I have magnesium 2 ion with copper solid. Remember, we'll give those lone metals, non-ions, a 0 as far as my oxidation number. We can throw those in just for practice. So now we can write the redox. Now let's really thinking about this for a minute. Is the 0 going to a +2 losing electrons, or is the +2 going to a 0 losing electrons? And Mr. MoNaCo has thought about this and decided that 0 going to a +2 is, in fact, losing electrons, and he's right. And that's it. Notice our charge is not getting smaller. Our charge is not being reduced. Another trick to figuring that out. So the opposite reaction is the reduction reaction. A +2 plus 2 electrons is gaining. Oil rig, gaining. And if I gain electrons, I become more negative or smaller. And 0 is smaller than +2. If I lose 2 electrons on one, I got to gain 2 electrons on the other. And now, since I've been talking so much, I'm just going to keep it up because he hates this part.
Yeah, this is Milks. Tell him what's the right answer
here we go.
to put on the reducing and oxidizing agent.
Here we go. So, if magnesium 0 solid is being oxidized, it is also, in fact, simultaneously the reducing agent. Okay, because he is the guy responsible for the reduction. If he's going to lose electrons, then he's responsible for the other guy gaining, and vice versa. And we've of course set these up nice for you that the oxidation is the reducing agent and the reduction is the oxidizing agent. I don't think we switched them up to trick you up, but we could. Ooh, we could.
Be nice, John.
All right.
Come on.
All right.
Carrying on.
All right. That's it.
That's it.
That's it. Those are the parts.
Yeah.
We got the electrodes. We didn't circle them much. We saw the salt bridge.
Yeah, it's the U-tube.
See that U-tube? And in this particular case, the switch is not closed. Once that switch is closed, we have a circuit. You will also see the voltmeter up top. That could be a light bulb.
Or a calculator or a computer
Or
whatever
any resistor, we call that in chemistry. In physics.
The point of this lecture is not to have you understand every intricacy of a battery, but to expose you to the basics of what you're expected to do. The practice associated with this is a simulation. It's very important to see what's happening at the anode and the cathode, see how the electrons and ions are moving.
It's almost like a pogo slipped right in.
It is. And when you're doing those practice pages, I suggest you actually use colored pencils to bring it to life a bit, because that will help certain parts of your mind understand what's going on.
There you go. So now we need to be able to take these important pieces, the electrodes, the salt bridge, all this kind of stuff, know where it is, and be able to identify it.
Yep, thank you.